Hi, everyone. Feel free to come on up close. So obviously, I'm not the person on the sign outside. Well, maybe that's not obvious. But if you look at the title of the talk, it's clearly not what was on the sign outside. So there was last minute cancellation. I was asked to fill in. So with a completely, totally different topic. So welcome. My name is Guy Royse, and this is Dungeons, Dragons, and Graph Databases. I am a developer advocate at Redis. There are 3 things on this slide that matter. One of them matters to my boss, one of them matters to me, and one of them matters to you. The thing that matters to my boss is that Redis logo right there. So he has sent me out to tell everyone that Redis is more than just a cache, it's more than just get and set. You can do a lot of different things with Redis, and so my mission is to get you to look at Redis differently. And so that's what the talk is today. We're going to talk about graph databases in Redis. It's probably something you're not aware that Redis does. We're going to talk about graph databases in general with a little tiny bit of Redis, just to be clear. The thing on this slide that matters to me is that Twitter ID. Maybe a little less than it used to, but it still matters to me a bit. And so, you know, I've been judging my value of my worth as a human being by the number of followers I have on Twitter. And so if you follow me, you can help me grow my self-image or narcissism, whatever you want to call it. And the thing that matters to you on this slide is the github.com/GuyRoyse. That is where all the source code's at for all the stuff I'm going to show you. And the slides are out there and everything too. So that's the thing that actually matters. All this other stuff's just fun. And so I'm a developer advocate, but in addition to being a developer advocate, I'm also a player of Dungeons and Dragons. How many people here play Dungeons and Dragons? Okay, how many people play Pathfinder? You're my man. And so I thought I'd share my character sheet as well as a player here. And I've got a whole bunch of jokes that I can make about this character sheet, but there's really only one that really matters. And that is that if you look in the bottom right, you'll see that my intelligence and wisdom are an 8, and my charisma is a 16. And it tells you everything you need to know about the talk you're going to see today. All sizzle, no steak. As a player of Dungeons and Dragons, I have a problem. I need to level up my character. I need a power game. And to do that, I need to go into the dungeon, find the best rooms in the dungeon. The best rooms have monsters that are at an appropriate challenge rating, appropriate difficulty that I can defeat them and get experience points and level up, and have the most treasure. And so, you know, as a player, you go into the dungeon, you wander around, and you kind of get what you get. But I thought this isn't optimal. I want to optimize this experience. So I could take, you know, this dungeon and figure out the best way to go through it. And as a player, I'm like, well, I'm also a developer, so I should build a database. Like put all the rooms and all the treasure and all the monsters in the database, and then I would be able to query it and figure out which rooms I should go to next. And that then begs a question. What database am I going to use? What kind of database? I could go with the default answer, which is a relational database with the rows and the columns and the one-to-many relationships. Or I could use a graph database with the nodes and the edges and the relationships and all this interesting stuff. So that's what the talk today is I'm basically going to compare and contrast relational databases to graph databases so that you can take something that you're probably familiar with. How many here have used a relational database? Should be damn near everybody, right? We've all written, you know, delete from without a where clause and regretted it. How many here have looked at graph databases before? A few of you, okay. Cool. So the first question is, what the heck's a graph database? So there may be some of you that came in here and thought that I'm talking about GraphQL. That happens quite a bit actually when I give this talk. So they see graph and they're like, oh, GraphQL. It's like, no, that's not what this is about. But don't worry, graph databases are still really cool. And they actually play really nice with GraphQL. But this is not a talk about GraphQL. Graph database is a database. It's where you store stuff. But to really explain what a graph database is, I think I need to tell you what is a graph first. And so this is where the mathy stuff comes in. And I want to qualify all this with, I am not a mathy person. Remember the intelligence of 8, the wisdom of 8, the charisma of 16. Math is not something that I've studied in depth, but I've sort of gotten enough graph theory that I can use a graph database. And so I'm going to share with you what I've learned, but I'm far from an expert. A graph is a set of nodes and edges that connect things together. It's a bunch of relationships and the points that bring those relationships, points on those relationships that represent all sorts of structures. You can use them to represent relationships between people, like a social graph, or logistics networks, or transportation networks, or polyhedrals. This 20-sided die is a graph. Graphs are made up of vertices, which are the points, or the nodes, and they're made up of edges, or the relationships, or the connections. And so this Platonic solid is a graph. The simplest graph is the null graph. Isn't it glorious? Yeah. Mathematicians argue about whether a null graph is actually a null, but I'm a JavaScript developer, so I just was wondering about the undefined graph as well as the null graph. And what happens when undefined triple equals null? Is that a thing? So null graphs are kind of boring. It's a graph with nothing in it. So let's add some nodes. This is also a graph. It doesn't have any relationships, it just has nodes. It's all points floating in space. It always feels like the beginning of Genesis, like creation. It's like, formless and void. There's just all these points floating out there, but there's no relationships between them. There's no sense of space. They're just out there. Now, you could argue that this is a set, but there are nodes and they're there. Let's add some relationships. Okay, now this is looking like there's some information in here, right? We had just a sort of a list of things that were out there. Now we're relating them. We know that A and D are connected to each other, and B and F are down there being best friends. And so this is a valid graph. Portions of this graph are what we call isolated. So node E, it's out there by its lonesome, it's isolated. But subgraphs can also be isolated. So B and F, even though they have a relationship to each other, don't have a relationship to anything else. There's no connection between those two nodes, no edge. There is a relationship between those two nodes, but they're not connected to the larger graph. So it's isolated. And in fact, any portion of a graph that's not connected is going to be isolated. So even the big part in the middle, the part you would think of as like the main part of the graph, is isolated. Let's connect all the nodes together. And now we have what we call a connected graph. A connected graph is where every node has a path to any other node in the graph. So from node D to node F, I have a path that I can get. I have two of them, actually. You can go through A or B, or you can go through A, C, and B. And so this is a connected graph. A fully connected graph is one where all of the nodes connect to all of the nodes. So this particular one here is, I'm just showing a subgraph of that larger graph because it looks prettier on the screen. But if you've ever seen the big circle of nodes like on a network diagram, and then you got all these cords that go across it, and every single thing is connected to every single thing, that's a fully connected graph. A 5-pointed star in a pentagon is a fully connected graph. So this is a fully connected subgraph. Every node connects to every node. Graphs can be undirected. All the graphs we've looked at so far have been undirected. This means the edges between the nodes they don't have any additional information on them. It's like a friendship. Either you and I are friends or we're not. I can't be your friend without you being my friend. Maybe in certain dysfunctional senses, but friendship is a mutual thing. It's like Facebook. On Facebook, you're friends with someone, and they're friends back. It's an undirected relationship. But you can have directed graphs, which have, a direction. I've given this talk for a couple of years now, and I've tried to come up with a better word to describe directional and directed and directionality other than direction, and I can't define it without using the word to define it. So we're just going to go with it has a direction. These relationships go from one node to another. This is like Twitter. So if I follow you on Twitter, you don't necessarily follow me back. And so that is a directed relationship. Or I always like to think of the relationship between like a parent and a child. Like my mother gave birth to me, but that relationship has a natural direction to it. So it's just extra information you can put into a graph. When we're looking at the nodes of the graph, we can query them and ask questions like, what's the degree of a node? The degree is the number of relationships it has going in or out, or it's just a total number of relationships. Directed and undirected graphs can both have degrees, or the nodes in them can have degrees. You can also have an out degree, which is how many outbound connections you have in a directed graph, or an in degree. And so these are ways that we can talk about about graphs, just sort of vernacular terminology, how to think about them. One last thing here is that anything can connect to anything. So there aren't any rules. You'll see here in this graph, I've got node A connecting to node C, and node C connects back to it. Node A is connecting to itself. The lines can cross. It's not Ghostbusters. You can cross the streams. It's safe because this is just a piece of paper. There's no rules about anything can connect to anything. So that's graph in 5 minutes. So far, so good? Excellent. This is the sum total of my knowledge of graph theory. Thank you for attending my TED Talk. So a graph database is when you take that structure, that graph data structure, and then you apply meaning to the nodes in the relationship. So the nodes become nouns in the system, and the relationships become verbs in the system. And so you start putting data over top of them. So our nodes aren't just nodes now. Now they represent the rooms and the monsters and the treasure in our dungeon. And those can have labels on them to tell you what they are. So you can have like a monster label or a room label or a treasure label. And nodes can have multiple labels. And you can add properties to those nodes, things you might want to query. Like up here we have Alice the elf with an ID of 4, challenge rating of 7, and she's worth 350 experience points. And you have Bob the ogre, challenge rating 5, worth 250 experience points. I suspect they send messages to each other. So, fun fact, it's fun to me anyhow, is Alice and Bob is actually my grandparents' name. I used Alice and Bob as examples for years, and then it struck me one day, well, that's my grandma and grandpa. I suppose you could describe my grandmother as being rather elfin. My grandfather was certainly not an ogre. He was a very nice old man. I actually miss him quite a bit. So you lay the data on the nodes. You can also put types on the relationships. So now we've got rooms that contain monsters and contain treasure and that lead to each other. And you can put data, in addition to a type on the relationship, you can also put additional properties on them as well. And then you've got a database that kind of looks like your problem domain. This is what I think is exciting about graph databases is the data that I model looks like how I think about my problem domain. When I'm using a relational database, I tend to, you got foreign keys and it doesn't quite work the way I think about the problem. And so this feels very intuitive to me. Nodes tend to represent items, usually nouns. They can have labels for the kind of thing they are, like room or treasure or monster. And they have attributes like name and challenge rating, experience points, and gold piece value and stuff. And they can just be by themselves. They don't have to have relationships. They can be fully isolated, and a node can be isolated. Relationships, or edges, represent a connection between two nodes. They have a type, they have a direction, and you can optionally put attributes on them. But most importantly, sorry, they cannot exist without the nodes. So if you're going through your database and you're like, I'm going to delete this node from my graph, the relationships go with it. Because you have to have two nodes, and if you get rid of the nodes, it goes away. 2 points determine a line. And I've sort of alluded to that they're like nouns and verbs, but I feel like I'm doing graph well when my relationships read like sentences. So I've got, a subject is the room. I've got a transitive verb in the middle, contains, and then the direct object, monster. So the room contains a monster. I suppose you could flip that around and say the monster is contained by a room. But my English teacher always told me that the passive voice was to be avoided. So that's theory. We spent about 15 minutes on it. Let's look at the actual problem, because I've still got the problem. I still need to find the best rooms with the best monsters and the best treasures so I can level up my character. And I need to decide if I'm going to use a relational database or a graph database. Spoiler alert, it's going to be graph. And so let's look at like some actual code. We've talked about sort of the idea behind these and how you can think about graph database, but how do we actually talk to a graph database? Well, how do we query it? How do we insert things? How do we remove things? Well, how do we do that with relational database? We've got a language, right? SQL. We've all used SQL, right? Even if we've used like an object mapping library, an ORM library, we still have to learn SQL. SQL is the only language I learned in college that I still use. And I went to college in the 90s. Well, in 90, yeah. Well, there's a language like that for graph databases. It's the one used by Redis Graph, and it's also was created by the folks at Neo4j, called Cypher. And Cypher is, I think it's kind of a beautiful language, if I can be so sappy as to say that, because it's a query language, but it's got like an ASCII art quality to it. And so you're all looking, you got your first tentative glance at syntax, you're like, what's it do? What's it do? What's it do, right? Well, the heart of Cypher are these matchers in the middle, these pattern matchers. And so you see that you got the word match, and then you've got this ASCII art looking thing, and then some return stuff. Well, that matcher is designed to look like a graph. It's the ASCII art piece. And what this matcher does is it goes through, you can use this to match this pattern in the graph. And so if you say match this pattern, it will return all the occurrences that match that pattern. And so this right here matches a node. It's got parentheses on it, right? It looks kind of roundish. It matches a node with a label of room. And it assigns it to the variable r so that you can use it later, so you can refer to it later. Over here, we're matching a node with the parentheses again, with a label of monster, and assigning to variable m, so we can reference it later. And then here in the middle is a relationship, and you'll see that it's actually an ASCII art arrow. It's pointing to the right. It's showing the directionality. And then it's got in square brackets the type of that relationship. And so if we were to use a match statement with this, it would find everywhere in the graph where we have the pattern room containing monster and return it. We could also use it in creating as well. We could create a room that contains a monster. It worked both ways. So let's see this in action. We're going to go through the basic CRUD operations. I'm going to show you the SQL. I'm going to show you the graph Cypher query, and so you can sort of see how they compare. So creating a room in a relational database for our dungeon. First off, I'm assuming that we've created all the tables already. So the tables have a schema, right? And so I'm inserting into that room an ID and a name and providing it values. We've done this a million times. In graph, we call create, and then we give it a pattern that we want it to create. So here we're saying create a room node. Assign it to variable r so I can mess with it later. And then we call set, and then we tell it the properties that we want to set. So set the ID to 1, set the name to statue room. This will create a new node, assign it to the variable r, and then hand it off to us so we can start setting properties on it. And the key thing here is that this is not, there's no schema. It's just whatever property, it's a bag of properties. So a node has properties, they're arbitrary. They're almost like a document. Whereas with a relational database, you have a schema. Pros and cons to both of those approaches. Obviously, people argue about whether typed or loosely typed or strongly typed languages are better. It's a trade-off. But Cypher and Redis Graph and Neo4j are all doing the untyped, schemaless kind of stuff. So create room, set some properties on it. If we want to read a room from a relational database, we use the select statement. This is probably the first thing you learned when you learned SQL. Select star from users where clue greater than 0. To do this with a cipher, you say match, and then the pattern you want to match. So I want to match all the rooms, all the nodes that have a label of room. And then I use a where clause to filter it down. So match our room where r.id equals 1. So it should give me exactly 1 result, and then I return it. And this match where is going to repeat here for the next couple operations. And I actually like this about Cypher because it's more consistent. SQL has always struck me as sort of like create was sort of its own thing, and update was its own thing, and insert and delete were all their own things. They all worked kind of differently. Cypher feels a little more consistent for me. So let's update a room. Update rooms, set some properties with a filter. Make sure you put that where clause on there. Because I've never done that in production before. Here we have that match where syntax again. Match the rooms where the ID is 1, but instead of returning the room, we're setting a property on it. We are, in this case, we're updating the property name from statue room to statue hall. We're getting an upgrade. It's got more than one statue now, so it's a hall. And if I wanted to add new properties, I could just specify them here. I could say set r.trapped equals true, or set r.is20 by 20 equals true, things like that. And there's syntax for deleting as well, so you could say where r.id equals that, and I think the syntax is delete r.name. I haven't done it in a while. I need to go look, but there is a syntax to do it. I just don't remember what it is off the top of my head. To actually delete the room node, in essence, delete the record. Delete from rooms where ID equals 1. Even more important, to put the where clause on the delete queries in SQL. To delete a node with Cypher, again, it's match where. So we're matching rooms where ID equals 1. But instead of returning it or setting properties on it, we're deleting it. So that's simple CRUD operations in Cypher. There is some alternate syntax. So I was using this match where syntax, but you can actually inline it. So the matching syntax has an option for properties. So if you put it in curly braces and then say ID:1, comma, name, and then in quotes, whatever the name is, that's going to match all rooms, all nodes with a label of room that have an ID of 1 as a property and have a property with a name of whatever the name is, and whatever other properties you want to specify. And that syntax in those curly braces is it's the same syntax you would use in JavaScript if you were just defining like an object. Create has an alternate syntax as well. You don't have to create a node and then set properties on it. You can use that same pattern to just create a room with properties already on it. So I can say create :room. Notice I'm not assigning it to a variable here because I don't need to mess with it. And I just provide the properties in line. So these are other syntaxes that are a little more useful, honestly. And here I am creating a monster using that syntax. Notice the lack of M on there. And here I am creating a treasure. And in the treasure one, I did both, because you can mix and match these. So I'm creating a node with a couple properties on it, assigning to the variable t, and when I've got that variable, I could set more properties on it. So I am. So here's our relational database so far. We've got some tables, no relationships. Here's our graph database so far. We've got some nodes, no relationships. I think we need some relationships. Let's put a monster in a room. So if we have a relational database and we want to change its functionality so that monsters can be put into rooms, the first thing we have to do is alter the table. Add a foreign key to the monsters for the room ID, and then insert or update those records to say, Alice the elf is in room 1, the statue hall, and Bob the ogre. So grandma's in the statue, hanging out with the statues, and grandpa's hanging out with the guns. And then we issue those updated statements, we're done. So how do we do this with a graph database? How do we do this with Cypher? we have to match the two things we want to relate to each other. So here I'm matching a room with an ID of 1, monster with an ID of 4, and then I reference those variables and use a create. So I say create, and any part of that create that match, that pattern you have in the create, if it's just a variable, it'll reference the thing that you matched earlier. If it's not, it'll go ahead and create it. And so this will create the relationship between the nodes without creating new nodes. If I try to inline this all and say create r:room with all the properties contains monster with all the properties, it would create me new monsters, new rooms, and the relationship between them. This one lets me link things that exist together. So that's how you put a monster in the room. You just create a relationship between them. Same thing for putting a treasure in a room. You alter the table, update, and then you match and create. So now our relational database looks fairly traditional. We've got a room. It has two one-to-many relationships, one to treasures. A room can have many treasures. A room can have many monsters. Our graph database has some relationships between the nodes. So room 1 has a monster in it. Room 2 has treasure in it. Room 3 has a monster and treasure in it. So we've got enough, we can start doing some queries and be a munchkin and select the best rooms, and so I can level up my character. I was supposed to say those things with these slides. So let's look at a query to farm all the XP. And let's look at that with SQL. Now, the easiest way to do this is naive. This is because this is going to give us the Cartesian product of the rooms table and the monsters table, and then we're filtering it out. So there's more performant ways to do this. But this is the general idea of how do you get all the rooms and monsters in them. Right? We want to find the rooms that have the best monsters with the best experience points so we can level up faster. So we select all the rooms that have monsters in them, we join on them, we filter them, and then we order them descending so that the biggest number comes to the top. And so now we've got a prioritized list of all of our monsters based on that we want. Go kill the most expensive monster first, that we can get the most experience points, right? With Cypher, we can do a match. And so instead of matching on just a node, we're matching on a full pattern, the room that contains a monster. And that's going to go through and match everywhere that a room contains a monster. If a room contains 2 monsters, we'll get 2 results. The room will be duplicated twice. And then we return the ID of the room, the name of the room, and the XP value of the monster. And then we order it by that XP value descending. And that will give me that same prioritized list, but with Cypher. Gold works a similar way. Same query. I just put these in here for completion. But we're just doing treasure instead of gold. Or treasure instead of monsters. So far, so good, but so what? I haven't done anything with a graph database that we can't do with a relational database. There's no reason to think one should be any better than the other. In fact, if you really like having schema, you probably are hating graph right now because it doesn't provide that. Well, what gets interesting with graph is when you connect rooms to rooms. When you take things that are of the same type, the same labels, connect them together. So if I wanted to have show the relationships of all the rooms, so what rooms lead to other rooms in a relational database, how would I do that? Well, I'd need to create another table that represents all the connections. And then it would have 2 foreign keys, both to the same table. The connection, the corridor that goes from the room and where it leads, and then vice versa. And then I would need to insert a bunch of values into that connections table. You've probably done this pattern as well. These are hard to query. I mean, unless you like recursive CTEs. I don't think anyone does. So these are hard to query. How do we connect rooms in a graph database? Exactly like we connect anything else in a graph. We query the 2 nodes. It doesn't have to be a room and a treasure. It can be a room and a room. And then we create a relationship between them. So it's exactly the same syntax as putting a monster in a room or putting a treasure in a room, is connecting these rooms together. And this is, I think, the cool thing about graph that really distinguishes it, is that it's really good at representing these relationships between like things. So here's our relational database so far. It's actually gotten kind of complicated. It barely fits on the screen. And here's our graph database so far, database worthy of Mordor. So we've got these in place. Let's do some more interesting queries, things that are easy to do in graph that are hard to do with SQL. And one of the things that graph has is variable length relationships. So I can say, give me rooms that connect to rooms, that connect to rooms, that connect to rooms, that connect to rooms, that connect to rooms. Give me long, arbitrarily long paths through the graph. So there's a matcher for that. This matches a room, this matches a room. And that little asterisk right there matches multiple relationships. So it's like n number of relationships of type leads to. So a match of room leads to room, room leads to room, leads to room, leads to room, leads to room, and so on and so on. You can limit these, because if you have a really large graph and you say, give me every path through the graph, that might take a while. Let's say you had 100 nodes and they had a bunch of connections to each other. You know, how many relationships, how many paths through there could you have? Actually, there could be an infinite number of paths if they're in a circle. Cypher will check for that. Yeah, question? Yeah, so the question is does it have to be of the same type? And it doesn't. So I could have a room and like a chamber and a corridor, and it could be leads to. Actually, if you notice the room contains monsters and it contains treasure, but the contains relationship is of the same type. And so you could actually do a query that says, give me all the rooms that contain anything, and then get the anythings back, whether they're treasure or room. So it's actually quite powerful. So here we've got a limit here. So we've given it a lower and upper bound. So say it has to have at least one, but no more than 3 hops. That's all this is doing. So you can scope it. You know, it's like, well, if the thing's 10,000 hops away, I don't care. I just want stuff that's nearby. And so you could do a simple query like, find all the nearby rooms. So I'm in a room, where could I go next? Give me rooms that are 1 or 2 hops away, and return me the ID and name of those rooms. Or I could find the nearby room with the most gold. Here I've got a more complex pattern. I'm assuming I'm in room 1, and I want rooms that are 1 or 2 away, and those rooms have to contain a treasure. And so this matches room to room to room to treasure, or room to treasure. And return the ID of the name and the gold piece value in the room, sort it descending so the biggest gold piece value shows up at the top, and limit it to 1 so I just get the first row. Now I have the next nearby room that has the most gold. That would be a useful query if I was a D&D player in a dungeon. Actually, I'm totally lying. The DM knows all this information. I'm clearly the DM. I don't play D&D, I run D&D. The other thing you can do with these is that path, you can capture it. So here, if I take a match and I take the results of that match and assign it to the variable p, so match p equals, and then room leads to star room, that's going to give me all the paths through the graph. And then I can use that path and ask and call functions on it. Use it as an argument in function. So I can get all the nodes in that graph, I can get the length of that graph, and then I can find like the longest path through that dungeon. So now this is a really, really slow query, because if you've got even a short number of nodes, a small number of nodes, there's a lot of permutations that you could have here, depending on your graph. So, but this is the way you can do it. I guess this solves the traveling salesman problem. Sort of. Probably not very well, but. We can also use with clauses as like aggregators in SQL. So here I'm matching all the nodes of type treasure, or with a label of treasure, and then I'm getting the max gold piece value out of all of those matched nodes and assigning it to a variable. So that's that first line up there. Then I'm finding all the rooms that contain treasure where its gold piece value is equal to that max. And that's gonna give me the one or more rooms that have the maximum value. And then I'm returning them. So that lets me find the room, or perhaps the tied rooms with the biggest treasure. And you can put all of these together to do crazy stuff. And this is the slow way, but this will find the shortest path to the room with the most gold in the entire dungeon. So we're doing that match to get that maximum gold piece value. We're then looking for all the rooms that contain treasure where it has that max gold piece value. That gives me the room I want to go to, the destination. I then match all the paths in the database, starting with the room that I'm currently in and ending with the room I want to go to that I've just identified. And then I return the nodes and the length of that path. So that gives me the path that I want to follow. And then I order it by length ascending. So the shortest one comes to the top, limit 1. Now this is the slow, stupid way to do this, but it does work. And on my MacBook, I'm able to run it in about 16 milliseconds. When I tested it this morning in the speaker room. The better way to do this is using a function. We've got a shortest path function in Redis graph that you can just pass in the pattern and it will return the shortest path for you. And this is doing something similar, but faster. So let's do a demo. You want to see this be real? Okay, I've got 8 minutes. We'll be fine. This is fine. So I've built a crazy random dungeon generator thing. And this is that big enough for everyone to see? Probably not. There we go. It feels a little too big. So I've got this little generator, and you can go look at the generator code yourself. It's a bunch of JavaScript code. I mean, if you want to look at bad JavaScript code and cry at night, you can go look at this. But the key thing I have here is well, let's just run it, right? So we'll do npm run generate. So that has just created a new random dungeon in a graph. If I go out to this tool here, Redis Insight, this is just a Redis client that's out there on the interwebs for free to use. You'll see that I have a node here called dungeon. It's 40 bytes. It's very small, actually, very compact. And if I go out here and query it, I can go ahead and look at it. Let's do a match. And so if I just match node with a variable and don't give it a label, it will return all the nodes. So this is sort of like a select star for a graph. I do match n, return n, graph.query, there we go, dungeon, then in quotes, like that. It will return all the nodes in the graph visually. I mean, I can get a text representation of these results as well, but this is cooler. Let's do a slightly better one. Let's do match. So I've got a node in here called dungeon, and let's name that D because it's a dungeon, right? Because that's the most important thing to do right now. So now I just get the one node that is the dungeon. And it's got a random name. It's the Forlorn Delve of Dala. I don't know if I like that one. Let's generate a new name. Okay. And then rerun this query. Now it's the Lonely Delve of Thaled. Thaleld? These are hard to say. So if I double click on this, boom, there's all the relationships. It has exits and entrances. The entrance is a musty chamber. Like double click on the musty chamber, we can see that it has 3 treasure items. It has a chest of coins. Come on. It has another chest of coins. It has a -1 cursed longbow. And you can start walking all along the graph and looking at all the things that are in it. It's kind of fun, right? So, and if we go over here and look at the text, we just see you know, you got a more textual relationship of it, which is what you get back in practice. So let's switch to another view. I want to show you this in code. So I've got a little simple JavaScript demo here that is going to query this. So all it does is it creates a Redis client using Node Redis. And this is just bog standard connect to Redis code here. And then I build my little query. So this is matching dungeon return d.name. I return the name of the dungeon. And I got some other queries here to show. I call graph.query the key in Redis that contains the graph, and then my query, and then I just stringify the results as JSON. So let's go ahead and npm run demo. And we see that we get the JSON response back, but that is kind of a pain, so let's do this. If you've never used JQ, it's like sed for JSON documents. It's fantastic. And what it does, in this particular case, is makes my data readable. So I got the name, the Lonely Delve of Thaled, executed in 0.9 milliseconds, which is stupid fast. Let's go ahead and do something a little more interesting against this dungeon. We'll see if this works. There's actually a bug in my query where if I don't have any treasure that gets generated in my dungeon, the query dies. We'll see if, comment this one out here. There we go. There we go. So that is the slow shortest path query that I showed you earlier. It's going through, it's pulling all the paths and it's just sorting them by path length ascending. And you can see that it ran in 23 milliseconds. Let's do the one that actually uses the algorithm here. All this code's on GitHub for you to play with, of course. And we run it again. We get this, we should get the same result. No, we didn't get the same result. Oh yeah, it's showing the relationships as well. It is the same result. But this ran in less than a millisecond. So using optimized algorithms make things faster. Who'd have thunk it? So that's pretty much what I've got from a demo point of view here. I've got 2 minutes. That's plenty of time. So this has been a fun, ridiculous application for graph databases, but I think there's a lot of practical ones as well. It's using analytics a lot. Social networks are a logical way, graph mechanism. You know, relationships on Facebook or Twitter and social media, they're just naturally graphs. A genealogy is a social network extruded over time through your ancestors. I don't know what Ancestry.com uses, but if I worked for Ancestry.com, I would totally want to use a graph database. Transportation networks are an obvious solution. One of the things you can do with graph is you can put weights on the paths, and then you can say, well, give me the shortest path that's weighted. So this path might be less hops, but it costs more. And so that could be minutes of transit time or distance in miles. And logistics, where it's like, you know, this E. coli contaminated spinach was found at this store, and the graph tells us that it came from these farms. So you could query those graphs and find out where it comes from. And I actually think you can use it for practically any database, really. I mean, it's a very natural, noun-oriented sort of thing. It's easy to think about. There's no reason why you couldn't build any application with a graph database on the back end. If you want to play with graph yourself, I used Redis Stack. It's just open source Redis, the one we know and love, with some modules plugged in to extend it. Redis JSON, Redis Search, Redis Graph, Redis Time Series, Redis Bloom, and you can get it to this URL. It's all free, all open. And go check out our Redis stuff. We got a Discord server if you got questions. The tool I was using is called Redis Insight. It's a great client. It's a great GUI for Redis. And we've got free university courses, or classes at university.redis.com. And all of this is at this QR code. You can trust it. It will never give you up, nor will it let you down. And that's what I've got. I'm Guy Royse. Thanks a lot.